Secondly, if we multiply log normal variables, we preserve log normality. Because of the way they're defined, if you think about it intuitively, a log normal variable is an exponentiated normal. In the same way that addition is a friendly operation for normals, multiplication is a friendly operation for log normals. And it's a simple derivation relating to the definition of what log normal means. So if we have x1 and x2 are normal, and y1 and y2 are the associated log normals, namely they're the exponentiated normals, then in fact, what's the product of the two y's? It's just e raised to the sum of the two x's. Well, we know the sum of two normals is normal, so therefore, y1 times y2 is also log normal. We can also develop the probability density function of the log normal. And remember that basically what we're saying is that the log of y is normal. And if you look carefully at this density function, you can see, and of course this density function, because we're exponentiating a normal, by definition, for any normal value, we get a positive log normal variate. So the log normal distribution is supported, or another way of saying it, it's only defined for y greater than or equal to 0. And of course, the value at 0 is 0, and that comes from the limit of what happens as the normal x goes to minus infinity. And we'll see a graph in a moment. So at 0, it's defined to be 0 because that's the limit of this function. But look at this. Look at the form of that. It looks like the normal distribution. What are the differences? The differences are, instead of a normal x in the exponent here, we have log y. Well, that's sensible, right? Because the definition of log normal y is that the log of y is normal. So we have a log of y where we typically see the normal x. Now, because this, in order to have this a function whose integral is going to be equal to 1, think about what would happen if you made a substitution into the integral of this function. You would say, let x be equal to the log of y. And then dx would be equal to what? dy over y. So this term here, which you wouldn't see in the normal distribution, you would see the standard deviation and the square root of 2 pi. That's in the normal. But you see a y here, and that y simply is because of the functional form of the variable being the log of y. So in fact, if I make a substitution into this function, namely let x be the log of y, dx is dy over y, this just transforms this into the original normal distribution. Okay, so it's easy to remember this density function if you know the normal density function, in that you have a log y for the x normal variable, and you need a 1 over y multiplier in order to make the differential work out by substitution. And again, this is just language. This is the same as the probability density function of an exponentiated normal. If you asked what is the probability density function of an exponentiated normal, you would find that in fact it's exactly that same thing. So why is that? So let's imagine that y is log normal. And it has parameters m and v squared. So what's the probability that y is less than or equal to a? Well, by definition, y is equal to e to the x, right? So that's the probability that e to the x is less than or equal to a which is the same as the probability that x is less than or equal to log a. Now, we're assuming x is normally distributed, so we can write this expression down. This is, in fact, 1 over sigma, square root of 2 pi, and then we have to integrate from minus infinity up to the log of a, the density function for the normal. And so that's equal to e to the x minus mu over sigma. There's a minus a half out here. And I think that's all okay. Yes. So now we make a substitution. Let's let x be equal to the log of y. So we now have to then substitute dx is dy over y. We do the substitution, and we end up with the y comes out. So I have a y sigma square root of 2 pi. Now in this substitution, x is the log of y. When x is equal to minus infinity, what's y? Well, y becomes 0. So I have to think about my limits of integration. And when x is the log of a, y is a. So the limits of integration become 0a. And then I complete my substitution, and I get log y minus mu over sigma squared. And I'm sorry, force of habit, in this integral I used mu and sigma for the mean standard deviation of the normal. And I know in this module we're actually using m and v squared. But hopefully that will not be confusing to you. And what one sees is that this is, in fact, exactly the probability that the log normal is exactly equal to, this is now a log normal distribution, probability that y is less than or equal to a, given log normality. Now, as what we're saying is that the probability that an exponentiated normal is less than a is exactly the same as the probability that the log normal variate is less than a. So it's just a substitution.